So in this video we're going to go over how to determine or find the domain and range if we're given a linear model. So in the first example we have a model that models a student grade as a function of the number of hours they spend watching television. So we have grade as the output, hours watching TV as the input. What you want to do first, if you're trying to determine domain and range of a linear model, is you want to look at the intercepts of the model, because sometimes the intercepts can be very useful in determining the domain and range of the model. So first you want to find and then interpret the intercepts and see if they are giving you useful information about the model's domain and range. We went over how to algebraically find domain and range in an earlier video, so in this video I used GeoGebra to graph the model and find the intercepts for me. So this vertical intercept, or the grade intercept, on the grade axis, of course over here we have the hours axis, so grade axis, the intercept there is, the inputs are hours, so 0 hours TV time corresponds to an output of 110, and this is my grade measured as a percent. So the grades are given in percents and time is being measured in hours with this particular model. So this says that if we watch no TV we get a grade of 110% in the class. The second intercept has a 5.5, but the units on that 5.5 are hours, so this is 5.5 hours TV watching time corresponding to a grade of 0%. And then what we can do is think about these two intercepts and identify whether or not they make sense and could possibly establish a domain and range for us. So 0 hours of TV watching is definitely within the realm of possibility, and 5.5 hours of TV watching is definitely within the realm of possibility. A score of 0% in a class is within the realm of possibility, and a grade of 110% is within the realm of possibility if the instructor is giving extra credit. If the instructor isn't giving extra credit, then you can't get a grade of 110%. You could only get a max grade of 100%. So I think that these intercepts could give us a reasonable domain and range for the model if we assume extra credit is being given. So assume extra credit. And if we do that, then I think we could give a domain and range for the problem based on those two intercepts. So our domain needs to be our inputs. Our inputs are hours. So for the domain, we would say hours need to be an element of. The interval, well, we would be going from 0 hours of TV watching all the way up to 5.5 hours of TV watching. We wouldn't want to go past 5.5 hours on this model, because if we go past 5.5 we get negative percentages, and negative percentages aren't possible. So then for the range, we would identify what are the potential outputs, and the outputs go from 0% all the way up to 110%. So for our range, we would say the grades are going to be an element of the interval that starts at 0% and goes all the way up to a possibility of 110%. So again, we want to give the numbers in interval notation in ascending order from smallest to largest. If we don't assume extra credit is possible, then we would need to change the domain and range, and that's okay to do. So again, this just says up here, it says give a reasonable domain and range. That means come up with a domain and range that you can defend. There isn't always a right answer. So if we assume that there's no extra credit, then we would need to know, well, what hours can we do? And what grades can we get? Well, if there's no extra credit, the grade should run on the interval from 0 to 100%. 0% to 100%. That's the worst interval I think I've written in a while. So the grades would be an element of the interval running from 0% all the way up to 100% max grade. And we know that 0% is generated by 5.5 hours of TV watching. And then we would need to identify how many hours gives us 100%. So we go back to our model and our grade. If our grade is 100%, then this will equal negative 20 times h plus 110. So we would subtract the 110 from both sides, which would give us negative 10 on the left-hand side, equaling negative 20 over h. And then divide both sides by negative 20. Divide both sides by negative 20. And this is going to give us h equal to negative 10 divided by negative 20 is 1/2. And if we look at the graph, we could ask the question, does it look like 1/2 hour is corresponding to 100? And if it does, then it's a good indicator that our algebra is okay. So here I would say 1/2 hour would correspond to 100%. So that would be another reasonable domain and range for this model. In the second example, we have a model that gives the weight in grams of rainbow trout in the Spokane River as a function of their length measured in millimeters. So again, I would start off like I did last time. I would say, look at the intercepts. And here I use GeoGebra to generate the intercepts for the model. And clearly this intercept doesn't make sense. This is a trout whose length is 0 millimeters having a negative weight. And over here, this intercept has a trout whose length is 206 millimeters having a weight of 0 grams. So neither one of those two intercepts makes sense. So they might not be particularly useful for finding a domain and range for this model. So one thing that we could do is we could say, hey, let's think about length, and length is going to be our domain because that's our input variables. And we could say, what would be a reasonable interval for length to run from? Well, we could start at this intercept. We could say, hey, we're going to start with the length of 0, but we know we can't have a 0 millimeter trout. So we're going to do an open interval instead of closed and say, let's run from 0 up to some max value. And a little research on the internet is going to identify that kind of a max size on rainbow trout is about 45 inches, which is equivalent to 1,143 millimeters. So we could say, hey, let's run the length of the trout from 0, not including the 0, all the way up to 1,043, which is kind of a high-end length on a rainbow trout, and use that as the domain. And if we do that, what would the corresponding range be? Well, the range are going to be our outputs, so those are weights. So weights would need to run from, well, hey, 0 millimeters right here generated 206.11 grams for the trout. So open interval on 0, open interval saying that 0 generated a weight of 206.11 grams, all the way up to, and now we just need to know what number to put in here, but this output is going to correspond to an input of 1,143 millimeters. So again, go back to the model and say, hey, what is the weight if we input 1,143, putting the length in where L goes, equals 4.5 times the length minus 927.5, and the length that we're inputting is 1,143, and crunch that equals, so multiply 4.5 times the 1,143, subtract your 927.5, use a calculator if you need to, That's going to give you 4,216 grams as the weight that's generated by a length of 1,143. So we'll use that as our high end, 4,216 grams. So we have length running from 0 to 1,143, weights running from 206 grams up to 4,216 grams. Again, this isn't perfect. This is just putting a lower limit and an upper limit on trout length, and then looking at what weights are generated by those lower and upper limits. The model probably realistically isn't good over this range of lengths, and a better way to get a domain and range for this particular model would be to go and find the original data set. That was used to generate the model, and look at the smallest length and the longest length in that data set, and the largest and smallest weights in that data set, and kind of pin things in using the data set itself. But I don't have access to that data set, so again, I'm coming up with a reasonable domain and range, something that I can defend. Smallest length is 0, don't include the 0. Biggest length, 1143, that's an uncommon length. What weights are generated? Use those as your domain and range.